Dear students, in previous class we were discussing the series solution of first order linear differential equation. Now, in this class let us discuss about the second order linear equations and the sum of its properties. So, what is a second order linear equation? It is second order. Second order linear differential equation is of the form y2 dash plus p of x y dash plus q of x y equals 0, where p and q are the functions of x alone. So, let x equals x naught be the solution of this second order differential equation. The behavior of this x equals x naught heavily depends upon the behavior of the coefficients p of x and q of x. There is a crucial point here. If x equals x naught be the solution of this second order differential equation, that is y2 dash plus p of x naught or y dash plus q of x naught or y equals 0, then the behavior of this x equals x naught, the nature of this x equals x naught, that is heavily depends upon the behavior of the coefficients p of x and q of x. So, consider this p of x and the q of x. If this both p of x and the q of x are analytic at x equals x naught, then this x equals x naught is said to be, an ordinary point. So this is an important definition. X equals x naught, if x naught will be the solution of this given second order differential equation, then this x naught is said to be an ordinary point if both these coefficients p of x and q of x are analytic at x equals x naught. If any one of this, if either p of x or q of x or both of them are failed to be analytic at x equals x naught, which is not analytic at x equals x naught, then this x naught is said to be the singular point. X naught is said to be a singular point. The solution x naught of second order differential equation is said to be a singular whenever it is not an ordinary point. So when it is become an ordinary point, it become an ordinary point only when p of x and q of x are analytic at that particular point. If any one of them failed, either p of x or q of x or both, if any one of them failed to be analytic at the particular point x equals x naught means the solution, then that solution is or that point is said to be a singular point. Means the nature of x naught or behavior of x naught is heavily depends upon the behavior of p of x and q of x. That's clear. So moreover, if a point x equals x naught is said to be a singular point if it is not analytic, then this x naught is said to be a regular singular point. That is another concept. Regular singular, ordinary singular and regular singular. Only if x minus x naught into p of x and x minus x naught into p of x and x minus x naught whole square into q of x both are analytic at x equals x naught. Both are analytic at x equals x naught. Then x naught is said to be a regular singular point. If x naught is an ordinary point, then nothing to see. If x naught is not an ordinary point, then x naught becomes a singular point. If x naught, then the singular point x naught is regular singular point. That again depends upon nature of p of x and q of x. If x minus x naught into p of x and x minus x naught whole square into q of x are analytic at this point x equals x naught, then this x naught is said to be regular singular point. If any one of them fails to be analytic, means x minus x naught p of x or x minus x naught whole square p of x or both are failed to be analytic at x naught, then x naught is said to be an irregular singular point. So, in the starting session, we say that the behavior of x0 is heavily depends upon p of x, behavior of p of x and q of x. So this is the explanation. Means x0 is a singular point if both p of x and if any one of both p of x and q of x are analytic. If any one of them failed to be analytic at that particular point, that point is said to be a singular point. If x minus x0 p of x and x minus x0 whole square p of x are analytic at x0, then it is a regular singular point. If any one of them failed to be analytic at x0, then it is irregular singular point. So these are the four nature or the four behavior of this ordinary point, singular point, irregular singular point, irregular singular point. These are the behaviors of x0, and that is heavily depends upon the behaviors of p of x and the q of x. Okay. So consider a problem. Consider a differential equation. It is 1 minus x square into y2 dash, 1 minus x square y2 dash minus 2xy dash plus p into p plus 1 into y equals 0, which is nothing but called a legendary equation. That is a legendary polynomial. 1 minus x square y2 dash minus 2xy dash plus p into p plus 1 into y is said to be a legendary polynomial, and which is equal 0 is said to be a legendary equation. Okay. So consider this legendary equation. 1 minus x square y2 dash minus 2xy dash plus p plus 1 y equals 0. So let us check whether x equals 0 and x equals 0 and x equals 1 are ordinary or singular points with respect to this equation. So how? If you compare with this equation, what is p of x? Here p of x is minus 2x by 1 minus x square. And what is q of x? Q of x equals p into p plus 1 divided by 1 minus x square. Okay. When you compare the legendary with the standard equation, second order, then we know that p of x is minus 2x by 1 minus x square and q of x is p into p plus 1 by 1 minus x square. So immediately, when x equals 0, both p of x and q of x are analytic. Both p of x and q of x are analytic. Clear? When x equals 0, p of x is 0. When q of x equals p into p plus 1 by 1. So clearly it is analytic at x equals 0, means p of x and q of x are analytic at x equals 0, means x equals 0 be an ordinary point of this differential equation. Clear? When x equals 1, what happens here? When x equals 1, what is p of x? That does not exist. Minus 2x by 1 minus 1. What is q of x? Does not exist. Means at x equals 1, p of x and q of x are not analytic. They are not analytic means they are failed to be analytic, means the x equals 1 is not an ordinary point. So this x equals 1 is a singular point. Okay, x equals 1 is a singular point. So clear, x equals 0 is a ordinary point, x equals 1 is a singular point. When x equals 1 is a singular point, then let us again consider the regular singularity or irregular singularity of this one. So for checking the regular singularity, consider x minus x0. What is x0? 1. So what is x minus x0 into p of x? X minus x0 into p of x and x minus x0 whole square into p of x. If both are analytic at x equals x0, then x0 is said to be regular singular point. Here x0 is 1. So it is x minus 1 into what is p of x? Minus 2x by 1 minus x square. That equals, yes, it is x minus 1 means 1 minus x. So it is 1 minus x into 2x divided by 1 minus x square can be rewritten as 1 minus x into 1 plus x. So it is equals 2x by 1 plus x. So x minus x0 into px or x minus 1 into p of x is 2x by 1 plus x. Clearly which is analytic at x equals 1. Which is analytic at x equals 1. Okay. Again, consider x minus x naught. Consider x minus x naught whole square into q of x. X minus x naught whole square into q of x is x minus 1 whole square into, it is p into p plus 1 divided by 1 minus x square. Again, x minus 1 whole square means 1 minus x whole square. So 1 minus x into 1 minus x divided by, it is 1 minus x into 1 plus x into p plus 1. Okay. Again 1 minus x cancelling each other. But again it is 1 minus x into p plus 1 divided by 1 plus x. So clearly this should be analytic at x equals 1. At x equals 1 it is 0. So clearly it is analytic. So both x minus 1 into p of x and x minus 1 whole square into q of x are analytic at x equals 1. Thus x equals 1 is, here 1 is a regular singular point. So clear, x equals 0 is an ordinary point. Since it become an ordinary point, there is no checking about its singularity. But x equals 1 is not an ordinary point, means it's singular point. Since x equals 1 is a singular point, then we may consider the singularity of this x equals 1. Is it regular or irregular? Then come to this process. It is x minus x naught means x minus 1 p of x and x minus 1 whole square p of x. Both are analytic at x equals 1. So immediately we can conclude that this x equals 1 is a regular singular point. So this is the behavior of the solution of second order differential equation. Okay. Now consider the point at infinity. What about the point at infinity? Point at infinity. So consider the second order differential equation y2 dash plus p of x y dash plus q of x y equals 0. We may consider the largest value. If the x be the solution of this differential equation, if x takes large values, means x equals infinity. Means x takes largest, that is sufficiently large real number, sufficiently large value for this x. So, for large values of this independent variable x, then we change, that's only for the sake of argument, we change the given differential equation or the independent variable. We change the independent variable x to t by transformation x equals 1 by t. Consider the independent solution of this differential equation, it will be x. If it takes highest value, means sufficiently large values, then we may transform the given differential equation with this transformation x equals 1 by t. So, thus we write the given differential equation, we rewrite the given differential equation and obtain the transformed differential equation. In this way, it is y2 dash plus p of t into y dash plus q of t into y equals 0. By this transformation, x equals 1 by t. So, if x has only sufficient large value, means suppose x equals infinity, then the given differential equation, we rewrite the given differential equation by using this transformation x equals 1 by t. So the given differential equation transformed into as y2 dash plus p of t y dash plus q of t y equals 0. So the given differential equation is said to have a regular singular point at x equals infinity. A regular singular point at x equals infinity if it is a regular singular point at t equals 0. When t tends to 0, x tends to infinity. Because of this transformation, x equals 1 by t. So, the given differential equation has if x equals 0 be the, at x equals infinity be the regular singular point, then t in the transformed equation, t equals 0 be the regular singular point. Clear? So the transformation is so crucial, means if the solution has largest value, highest value, then the transformation is put x equals 1 by t. So we may consider. Now let us consider an example. So consider a differential equation x square y2 dash x square y2 dash plus 4xy dash plus 2y equals something. So what about the point x equals infinity? Is x equals infinity be a regular singular point or not with respect to this differential equation? So we consider this question. Consider the differential equation x square y2 dash plus 4xy dash plus 2y equals 0. Our question is whether this x equals infinity be a regular singular point of this differential equation. Whether it's a regular singular point or not. How? Since x equals infinity means x has a highest value, largest value. So with respect to that value, we may not say that this equation or x equals infinity be a regular singular point. So for the convenience, we just take a transformation, put x equals 1 by t. X equals 1 by t, so what is x square? 1 by t square. So what is dy by dx? Then dy by dx equals, by the chain rule, it is dy by dt into dt by dx. Okay, that means dy by dx means y dash. Y dash equals dy by dt. So it is dy by dt into dt by dx. What is dx by dt? Here x equals 1 by t. So dx by dt is minus 1 by t square. So its reciprocal is minus t square. So y dash is minus t square into dy by dt. And what is y2 dash or d square y by dx square? D square y by dx square is d by dt of dy by dx into dt by dx. Again by chain rule. That means y2 dash d square y by dx square means y2 dash d by dt of dy by dx. What is dy by dx? dy by dx is dy by dt into minus t square. So it is d by dt of now what is dy by dx? dy by dx is minus t square into dy by dt into dt by dx. What is dt by dx? It is minus t square. So that means it is equals y2 dash equals d by dt of minus t square dy by dt into minus t square. So it is t power 4 into t square into t square means minus and minus. So it is t power 4 into d square y by dt square y by dt square plus 2t cube into dy by dt. Okay, d by dt of this one. So it is by using product rule minus t square into d by dt of dy by dt is d square y by dt square. So plus dy by dt of dy by dt into this one minus 2t. So multiply with the minus 2t square. So it is y2 dash is this one. Therefore, the given differential equation 1 becomes x square y2 dash. What is x square? X square is 1 by t square. So it is 1 by t square into what is y2 dash? It is t power 4 d square y by dt square. D square y by dt square, maybe it is y2 dash. Represent this in this way. So plus 2t cube into y dash. This is x square y2 dash plus 4xy dash. 4x means 1 by t into what is y dash? Y dash is minus t square into y dash plus 2y equals 0. So that means 1 by t square. What do you get? It is t square y2 dash then plus t square by 2 dots plus 2t y dots, again plus 4 into minus t square, so it is minus 4t y dots plus 2y equals 0. So that means it is t square by 2 dots plus 2t y dot minus 4t y dots, means it is minus 2t y dots plus 2y equals 0. So it is t square by dots. It is multiplying with hence what is p of t? P of t equals, what is p of t? Minus 2t by t square, and what is q of t? It is 2 by t square. Okay, when it compare with the standard equation, what is p of t? Here p of t equals minus 2t by t square. Minus 2t by t square, and the q of t, what is q of t? Q of t equals 2 by t square. 2 by t square. So our aim is to check x equals, whether x equals infinity is regular or singular point. For instead of x equals infinity, it is transformed into a function in t. So when at t equals 0, both the p of t and q of t are not analytic. Why? Because they are not exist. Not analytic means t equals 0 be an ordinary point. T equals 0 be an ordinary point means, so t equals 0 be a, yes, clearly p of t and q of t are not analytic. Okay, not analytic, therefore t equals 0. At t equals 0, that means x equals infinity. Clear? So t equals 0 be a not analytic, hence then consider t minus t naught into p naught. Sorry, p of t, that is minus 2, and t minus t naught whole square into q of t, that is 2, hence t equals 0 be a regular singular point. Okay, that means x equals infinity be a regular singular point. Clear?